Brian will be doing a couple of segments in today's program called Try It. And so if you have a few items available, you might want to go grab them in the moments here before the program starts. I believe the things that will be most fun to have are pencil, a ball of some sort, styrofoam ball if you have it, and a flashlight. If you don't have it, by all means, you can just watch us today, but feel free to try that during the program or later on if you like. And there are also 2 worksheets that go along with today's program. So if you have your parents go back to the email that was sent or the Facebook link that was sent, those worksheets should be in the links. So keep your questions coming throughout the program. We're really excited that you all are here today. And I'm going to turn it over to Brian for Phases of the Moon. Thanks so much.
Great. Thank you so much, Crystal, and good morning, everybody. Thank you so much for joining us today. As Crystal was saying, my name is Brian Kohler, and I run the Planetarium, the Treworgy Planetarium at the Mystic Seaport Museum. I'm not sure if any of you have had a chance to come and visit us in the recent past, but if you know a lot about the Mystic Seaport Museum, you know that we are a maritime history museum. So we've got boats, we've got buildings along the coast, and kind of the theme of them is teaching what it's like to live and work on and near the water. And so the planetarium at the Mystic Seaport Museum was actually built 60 years ago, the original planetarium, and it was originally built for the purpose of teaching navigation, to taking a look at the stars and explaining how sailors would use those stars to find their way across the sea. So we do love teaching navigation. Maybe we'll do a future program about that. But today we're going to keep things very focused. And as we explore the moon today, we'll, for the most part, be talking about 3 objects: the Earth and the moon and the sun, because it's the relationships between those 3 objects that cause the moon to look a little bit different every night. So as Chris mentioned, there's going to be a flashing across the screen that will say, try it. And that's going to be your opportunity to participate in today's program. We might do some math problems together. We might do some outer space detective work. And so I can only see a couple of you on my screen here. But what I'm going to do is if I throw a question out, I'm going to ask you to see if you can type the answer into the chat box. And then I'll check in with my friend Crystal and see how the answers are looking. All right, sound good? Thumbs up if you're ready to go. All right, I'm seeing just a few thumbs up. That's good enough for me. All right, so let's start by talking a little bit about our solar system. Now, if you're like me, you might have a favorite planet. My favorite planet happens to be Saturn. And we could spend all day today talking about every single one of these planets, but we're going to focus on the moon today. So for now, just take a quick glance at this diagram of our solar system. We see the sun, we see those 8 planets. I even threw Pluto in there just for fun. I know Pluto is technically a dwarf planet, but he's still a pretty cool guy and everybody loves Pluto. So what I want you guys to notice in this diagram is the difference in size between all of these planets. You've got Jupiter, the biggest planet in the solar system, the king of the planets. And Saturn's pretty big with those rings. It's almost as big as Jupiter. Then you've got Uranus and Neptune, a little bit smaller. And then you have those 4 planets that are closer to the sun, what we call the rocky planets. So Mercury, Venus, Earth, Mars. See how small they are compared to Jupiter and to Saturn. So in order to be a planet in our solar system, you have to follow 3 rules, and you have to follow all 3 of them. Rule number 1 is that you have to orbit around the sun. Okay, all those planets do that, but so does Pluto. And so do all those asteroids in the asteroid belt. Well, rule number 2 to be a planet in our solar system is that you have to have enough gravity to form your shape into a sphere, into a ball. And that's where we get to rule out all of those asteroids because they're kind of shaped like potatoes. They don't have ball, spherical, round shapes to them. But we still haven't removed Pluto from the equation. And it's the 3rd rule of a planet that ultimately trips up our friend Pluto. Because in order to be a planet in our solar system, your path around the sun cannot be blocked by anything. So your path around the sun has to be clear, and that's where Pluto gets tripped up. And, you know, out there in the belt beyond Pluto, in that Kuiper belt region of our solar system, there are a whole bunch of Pluto-like objects. So people will sometimes ask me at the planetarium, will Pluto ever be a planet again? And the problem is, if you let Pluto back into the club, there's a lot of other objects we have to consider as well. So it's not a matter of do we have 8 planets or 9. It's more like, do we have 8 planets or 109? So for now, Pluto remains kind of on the outside looking in. But now that we've taken a look at these planets and we've talked about what makes a planet in our solar system, let's talk about moons. Every object you are seeing on the screen right now is a moon. I know when we hear that word, one object in particular comes to mind, but if a planet is an object that goes in orbit around the sun, then a moon is an object that goes in orbit around a planet. So even though Earth has one moon, there are over 120 different moons in our solar system. And they come in different shapes and sizes. They're made of different materials, which causes them to be different colors. Some of them have volcanoes on them, and some of them have huge craters as big as the Grand Canyon. They're very, very unique objects. So now we're going to do a little detective work. This is our first try it activity of the day. This is my chart of how many moons each planet has. Mercury and Venus don't have any moons. Earth has 1, Mars has 2, Jupiter at my last count has 79, Saturn has even more than Jupiter does, it has 82. And then as we get out to Uranus and Neptune, the number starts to go down again. So it's like this curve where the moons go up and up and up and up and up, and then as the planets get smaller, the curve starts to go down again. So I'm wondering, if I told you that the 2 things that determine how many moons a planet gets are how big the planet is and how far away that object is from the sun. If you could imagine this curve going up from 0 to 0 to 1 to 2 to 79 to 82 and then down to 27 and 14. So how many moons do we think Pluto has? You can go ahead and type your answer in the chat box if you want, and we'll see what kind of results we get before I share the answer. This is our outer space detective work here. We're gonna try and see if we can find a pattern. Crystal, you're on mute, but I hear you check it in.
All right, sorry, Brian. I was just reading for you from the chat box. I've seen 5, 6, 0, 47, 1, 3 or 4, at least 9. So lots of good educated guesses from folks.
Wow, really, really good ideas out there. Now, anybody who said a number between, say, 0 and 13, you kind of picked up on that pattern, whereas we go from Saturn to Uranus to Neptune to Pluto, the moons are getting smaller and smaller in number. Now, I did hear at least one person got the exact right answer, and I'm not sure if anybody else tried to guess this one, but the number of moons orbiting around Pluto is 5. So 5 moons, which you might be saying there, I know some of you guessed 0 or 1, and some of you might be saying they're going, well, hang on a second. Earth is way bigger than Pluto is. So how come Pluto gets more moons than we do? And it's that combination of size and distance from the sun that determines how many moons we end up having. The further and further away from the sun you get, the more we have these little rocks and little pieces of ice floating around space that can get pulled into orbit around a planet. The reason Venus doesn't have any moons, even though it's the exact same size as Earth, the reason Venus has no moons is because it's so close to the sun that if Venus had a rock orbiting around it, the sun would probably swallow it up. It would say, I'll take that, thank you. And it would just capture Venus's moon. Same thing with Mercury. We are just far enough away from the sun that we can put a moon in orbit around us and the sun won't steal it from us. And then we get further and further away, the moons get bigger and bigger until the planets start getting smaller. And then the number of moons goes down and down and down. And so we know for certain, because we've gotten very close to Pluto with a spacecraft with some pretty good cameras, we know for certain that Pluto has 5 moons orbiting around it. All right, Crystal, I'm going to check in with my friend Crystal here because we're about to move on to our next subject. Do we have any questions you want to bounce off me before we move on? Or
Nope, Brian, there are no questions from our audience so far, only some really great guesses from your last question. So
super, excellent. In that case, we'll move on to our next step, which is talking about how did we get a moon? Now, before I give you guys that whole big screen to look at, let me tell you the truth. I don't know. I don't know where our moon came from. Nobody knows, because for as long as there have been humans living on Earth, we have had a moon orbiting around us. There's no ancient cave with an ancient journal inside of it that says, "Dear diary, we got a moon today." It's been around as long as we've been around. So here's what scientists do when they don't know the answer. They come up with a theory. Some of you may have heard that word before in science class, and it's really important to note that a theory is not a guess. We're not just taking random guesses here. A random guess would be, I think Mr. Brian is wearing green today, which, by the way, thank goodness I'm not, because this is a green screen behind me. I'd be blending into the background. But that's a guess. That's not based on anything. Now, if you said, I think Mr. Brian is wearing white today, I'm actually technically wearing light blue, but all the lights in the room are brightening me up. But that's a good, educated guess. And it's a theory based on your observations. So, what is the best theory we can come up with for where Earth's moon came from? It's known as the impact theory. And it goes a little something like this. Many millions of years ago, long before there were people on Earth, even before there were dinosaurs on Earth, Earth was standing tall, minding its own business, and along came an object that we call the impactor. This rock was almost as big as Mars. And when that object crashed into Earth, it did a whole bunch of things. First off, it ripped Earth to pieces. Oh my goodness, thank goodness there was nobody living on Earth at this time. But over a really long period of time, Earth kind of put itself back together again. People sometimes ask me, how does an object form itself into a sphere in outer space? How could Earth go from being that 1, 2, 3, that 4th picture we see? How could it go from that to being a sphere again? And the way objects work when they're spinning around in space, it's kind of like the way that sea glass tumbles around in the ocean. If you've ever been walking along the beach and you pick up that piece of sea glass and it's super smooth and it's super polished, that's because that piece of sea glass spent years, however many years, tumbling around in the salt water. Well, there's no salt water out in space, but the gravity of space has those same powers to kind of put things back together again. So over a really long time, Earth fixes itself and makes itself a sphere again. Now, what about all those splinters from the impactor? Well, some of them drift off into outer space, but others can get captured by Earth's gravity. And the biggest piece ends up forming itself into a sphere to create our moon. It's a pretty good story, right? Now, in order for this to not just be a guess, I need to have some kind of proof, some kind of evidence. So the evidence for our impact theory on the moon, why don't you guys take a look at this diagram and check out what happened between the Earth at the beginning and the Earth as it is now. What's the biggest change that happened to Earth? It's back together again, it's a sphere, but there's one really big change. And the big change is that the Earth is now leaning. It's tilted. The Earth got knocked on its axis tilt. And what that does, it does something to us here on Earth. It creates our seasons. Seasons on Earth have nothing to do with how close to the sun we are. Earth's orbit around the sun is not a perfect circle. There are times when we are closer to the sun, and there are times when we're further away. Now, would you believe me if I told you that the month when we are closest to the sun is actually December? Yeah, In the middle of our winter time, we are as close to the sun as we can be. It turns out that seasons on Earth have nothing to do with that with the closest to the sun. They have everything to do with the tilt of the Earth on its axis. In the diagram you see right now, the northern half of the Earth, where we all live, is tilted away from the sun. So this is the time of year when Australia and Brazil and Antarctica, they're getting their summertime. Now, just last week, nope, it was 2 weeks ago, we had the spring equinox. So we reached that time of the year when the Earth isn't tilted towards the sun and it's not tilted away from the sun, but the Earth's tilt isn't leaning us towards or away from the sun. So eventually, we are now getting to the point where our days are getting longer. Summertime is just a few months away. And so the axis tilt creates those seasons. This leads to an interesting question. What if we never got hit by something? What if Earth never went from standing straight up tall to being tilted on its axis? Well, if that happened, every day on Earth would be pretty much the same weather. We wouldn't have really warm days. We wouldn't have really cold days. Every day on Earth would be 55 degrees and partly cloudy. Maybe not partly cloudy, but we wouldn't get the seasons that we experience. We wouldn't get snow in the wintertime, and we wouldn't get 95 degrees weather in the summertime. So the fact that we have seasons is pretty good evidence that maybe, just maybe, this impact theory is the best explanation of where our moon came from. Crystal, I saw you pop up there. You got something for me?
Yeah, Brian, I have a question coming in from Nate, and he asks, is the bell curve-like relationship with planet size and number of moons a common trend among other solar systems too?
Wow, that is a great question. Yes, absolutely.
I hope you know the answer because I don't.
Well, I can shed a little light on the answer because we have been looking at other solar systems. We have seen stars that have as many as 7 planets orbiting around them. So we do see that trend. It does appear that the objects that are closest to their home star are not able to have moons orbiting around them, because there are stars that are bigger than our sun, there are stars that are smaller than our sun, but all of those stars have so much gravity that they would swallow up any moons that were too close. And then it does seem that as planets get bigger and further away from their mother star, that the number of objects orbiting around them does seem to increase. So yes, that relationship that we see in our solar system has been seen in other parts of outer space. Great question. Very, very well done. Cool, I like that one. All right, so now we are going to talk about those 3 objects that are really related here, the sun and the earth and the moon. And I want to start by talking about a little bit of a size difference, because what you're looking at right now on your screen is the actual relationship between the sun and the earth and the moon if they were to scale size-wise with each other. So if I shrunk the sun down to be just that orange ball of gas you see over there on the left side of your screen, then the earth is that little teeny tiny white dot. And the moon is that really teeny tiny pixel. Now, I don't know about you guys, but when I go outside in my backyard, the sun during the day and the moon at night, they look like they're the same size, at least to my eyes. You know, it turns out that the sun is 400 times bigger than the moon. And it turns out the moon is 400 times closer than the sun. Now that is something that is unique. We have not found any planet in our solar system or elsewhere where the relationship between the sun and the moon are exactly a perfect balance, so that one object is 400 times further away, but 400 times larger. And that special relationship between the sun and the moon is going to cause a very rare, very unique event, which we're going to talk about a little bit later. But one of the best ways I found to explore this relationship between the sun and the moon and the earth is to use models. And some of you may have heard these kind of terms in your math class, talking about geometry and things like that. You might be familiar with the word that is called a diameter. Now, a diameter is a line that goes through the center of a circle. So if I were to take, where's my little model of the moon? Here's my model of the moon right here. Now, if I were to take one finger and put it on the top of my moon model, and if I were to take another finger and put it on the bottom of my moon model, that line that connects my two fingers, that's a diameter because it goes right through the center of that circle. If I were to pick two random spots on the moon and put my two fingers there, that's not a diameter because that line between my two fingers doesn't go through the center of that circle. So it's really important to know what a diameter is if you guys are going to help me with this math problem we're going to try in a little bit here, okay? So here's how the math works. The actual diameter of the real Earth is about 8,000 miles. I happen to have an inflatable model of the Earth right here. It's my beach ball Earth. It bounces. This model I'm holding in my hand has a diameter of about 12 inches. 1 foot is the diameter between the North Pole, the South Pole of that Earth model. The actual diameter of the real moon is 2,000 miles. So my little moon model here, which is to scale with my Earth model, in order to figure this out, I have to make a fraction. Hopefully you guys are good at fractions. So if 8,000 miles is the diameter of the real Earth and 2,000 miles is the diameter of the real moon, if 12 inches is the diameter of my model Earth, can anyone tell me what the diameter of my model moon is? If you know, go ahead and throw that number into the chat room right now. I'm going to have my friend Crystal take a look. Take your time, because this is a big fraction. It's going to take, I see some of you have got pencils and paper out, and you're going to try to figure this fraction out. So take a few moments, let you guys crunch some numbers, and we'll see how those numbers look.
Brian, I'm seeing a lot of 6, 3, and 4.
Ooh, okay, those are all really close. All and obviously
threes.
has to be smaller, right? Yeah.
Yeah, I actually see some friends of mine in New Jersey. They are saying 3, a lot of 3s, 5s, 4. Yeah.
Okay, well, those are all really close. One of those answers is absolutely right. So if you had guessed that my moon model had a diameter of 3 inches, you are right. That means the diameter of the moon is 1/4 of the diameter of the Earth. If I laid the moons across the equator of the Earth, I would need 4 of them to get all the way across the widest part of Earth. Good job with the math there, guys. That's a big fraction. Well done.
Hey, Brian, we had one more question coming in from the audience.
Okay.
How far away is the sun from us?
Ah, very good. The sun is 93 million miles away from Earth. So 93 million miles. When we talk about things traveling at the speed of light and this idea of a light year, which is how far light travels in 1 year, the sun is 8 light minutes away from Earth. And what that means is it takes light 8 minutes to travel those 93 million miles. And it means when you look at the sun in the sky, you're actually seeing it on an 8-minute delay. Now that's a little different from the moon, which is so much closer to us. The moon is 1 light second away from Earth, which means it only takes the light shining off of the moon 1 second to reach Earth. That's the little delay we've got, not nearly as big a delay as with the sun or with these other objects. Now, when we, just to finish that sort of sentence, when we talk about what a light year is, there are some stars. The closest stars to Earth are at least 30 light years away from us. So when you look up at night and see stars in the sky, you're actually seeing them on a delay because it takes the light from those stars anywhere between 30 to hundreds of years to reach Earth. The North Star Polaris is 400 light years away from us. So that light takes 400 years to travel from the North Star to Earth. So we get these delays because everything in space is so far away. Oh, I see my friend Crystal popping up. All
Hi,
right, what do
Brian.
you
We've
got?
got two more distance related questions. So
Okay.
hopefully you'll know the answers to these off the top of your head. But we have a question from Nora. How far is the moon from us? And then from Katie, how far is Uranus from us?
Oh boy. So I will tell you, I actually don't know those answers off the top of my head, but you know what I am going to do? I'm going to do a little bit of speed math here. I happen to have a calculator handy. And if the moon is 400 times closer than the sun is, I'm going to take 93 million and divide it by 400. That means the moon is about 232,000 miles away. So when those Apollo astronauts, we're going to talk about Apollo a little bit later, but when those Apollo astronauts traveled to the moon, it took them 3 days to get there from Earth, traveling in a rocket that was going pretty fast. So
Wow.
unfortunately, I don't know the distance from Earth to Uranus off the top of my head. I'm so sorry, but that'll
That's
be something
okay.
we can all Google together when the program is over.
Yeah, that's okay, Brian. And just a note for everyone out there, I'm going to be putting our email addresses up at the end of this program, and you're welcome to send these questions to us. But I also wanted to say, just for the sake of Brian being able to move on to the next bit of content for this program, we're going to actually at some point very soon have a program called Scaling the Solar System. So you can actually start to understand where all of these planets fall in the solar system and how far things are from each other. So stay tuned for that. Keep the good questions coming, and I'll do my best to answer the questions, and at the end we'll definitely give you our email addresses.
Awesome, super. All right, now we get to one of my favorite subjects because the one thing I enjoy, I love living near the water. I love working near the water. And if you're like me, I've noticed in the chat box, we've got a lot of visitors today from Connecticut, New York, New Jersey. A lot of us know what it's like to be near the coast. So if you live near the water, if you work near the water, if you just like going to the beach for fun, you might have experienced one of these quirky things about the relationship between the Earth and the moon. And that is what we call tides. So if you've ever gone to the beach before and you're walking along the sand and the sand is wet, and yet the water isn't coming up that high. So how did the sand get wet? Well, it turns out a little bit earlier that day, the water was moving higher onto the beach because water levels on Earth will rise and fall, and it has to do with the moon. Because the moon, just like the Earth, has some gravity to it. Now, we know Earth has gravity, right? If I jumped up in the air right now, I'd come back down again. And a lot of times when we imagine people walking on the moon, we picture those bouncing steps. And you might think that the moon doesn't have any gravity. It does, but the moon's gravity is less than the Earth's gravity. So we don't feel ourselves getting pulled by the moon, but little water molecules, they actually do feel the pull of the moon. So here's my very silly tides diagram here. This is a little bit exaggerated. I love that Crystal was just talking about using scale models in the solar system. This is not to scale. But if you imagine, this is a bird's eye view. We're looking down at the North Pole of the Earth. And I've got my little stick figure guy who's hanging out, and you can see how the water levels are getting stretched out. So the part of the Earth that is facing the moon is going to be getting higher tide, the water levels being stretched out by the moon. Where my stick figure friend is standing, he's getting a low tide because the water has to go somewhere. The moon can't create new water, it can just move the water around the Earth. So if there are parts of the Earth where the tide is getting higher, the water level somewhere else has to go down. So one way to imagine tides would be to think of it like a clock. And so in this example, we are at the part on Earth where the big blue pole is sticking straight up, okay? So when our tidal clock begins, we are lined up with the moon and our water level is as high as it can be. So as the clock goes on, we're going to start to move the clock. The Earth is now rotating like it does over the course of one day, and the water level is going down. Eventually, we reach a point when we are perpendicular, a 90-degree angle between the Earth and the moon, where we are on the Earth and the moon. So now we have our low tide. Now, what's going to happen as the day goes on? Is the tide going to go down or is it going to go up? I'm thinking it's going to go up. So I'm going to keep that clock moving and watch the water levels getting higher and higher and higher. And eventually, when we're opposite from the moon, we've got our high tide again. Second high tide of the day. Now the clock goes on and on and on. We get our second low tide of the day. And when I finish up the clock, we go right back where we started. Uh-oh, what happened? 24 hours later, the moon has moved. Would you look at that? So 24 hours later, we're not back where we started. And you know what that means? It means that the high tide every day isn't going to be at the same time. The tidal period for most major bodies of water on Earth is not 24 hours, it's 24 hours and 50 minutes. So every day, whether you live near the Thames River or the Block Island Sound or the Atlantic Ocean, those bodies of water are going to rise and fall, and the time is going to be a little bit different every single day. But there are groups like NOAA who keep track of the tide tables. I actually make a list for my friends at the Mystic Seaport Museum so that our friends at the Sailing Center and in the shipyard, they know when the water level's rising and falling. So we can use these tables to figure out when the water is going to go up or down. Crystal, do you have a tides question for me?
There aren't any questions. I just wanted to let you know that there's some chatter in the chat box, and people seem to be interested and surprised that the moon has that much control over the ocean, which is kind of neat. And also, there's a person, I'm sorry, I just lost the name, who actually is learning about perpendicular lines in class. So thank you for showing us perpendicular line there.
That's my favorite thing about this program is we get to weave in a little bit of math and science. So I hope there's a little something for everybody in here. Now, I was mentioning all of us who get to hopefully live or work or get to vacation near the water. Now, you might not notice when you're sitting at the beach for a couple of hours, the difference in tides is going to be slight. Maybe the water will go up by a couple of feet, not a huge drastic difference. But there are parts of the world where the tides can be really, really extreme. These pictures, for example, are from the exact same place on Earth, a body of water in Canada called the Bay of Fundy. Now, the Bay of Fundy has 50-foot tidal swings. The difference between taking our fishing boat out to sea and not taking our fishing boat out because it's sitting on the ground, that's a big difference. So the reason why we get such extreme tides in that body of water is like a big bathtub. This is not a try-it exercise. I don't want anybody making a mess in your bathroom, but I want you to imagine with me that you have a bathtub full of water. And if you were to take your hands, put them in that bathtub, and slosh all the water towards one side of the tub, what's going to happen is the water is going to splash up on the side of the tub, and then it's going to come back down again. And then where is it going to go? It's going to splash up on this side and then come back down again. And it's going to splash and come back down, splash and come back down. So the moon is the hands. The moon in the Bay of Fundy is taking that water and sloshing it so that the high tide and the low tide and the high tide and the low tide, they're so extreme in those bodies of water. Now, we don't have any bodies of water here in Connecticut that have these kind of tides, but it's really interesting to see how there are people around the world whose lives, their jobs are affected by the fact that water goes up and down, and it is all related to the moon's gravity. Crystal, I saw you check it in there.
Yeah, sorry. So Katie also wants to know, does the tide move or does the moon move?
Well, it's a little bit of both. So the moon is orbiting around the Earth. That's why when the Earth made its 24-hour clock and we were back where we started, the moon wasn't in the same place anymore. So there's a lot of things that are moving, right? The Earth is moving around the sun. The moon is moving around the Earth. The water is moving all around the world. The ocean currents all around the world, brings water all around the world. But those water levels will be dragged up or down based on, good question. So my try it activity for the tides is one that you might have to do on the next bright day. I know we spend a lot of time at our homes these days. We have to do that because we have to be safe. But getting outside is kind of a nice thing every once in a while. So if you have a spot near, or you're nearby a lake, or you're nearby Long Island Sound, you could experience the tides. You could spend just a little bit of time walking around on the beach, and you'll notice maybe the water is coming all the way out. That means you're getting a high tide right there. Or maybe the water isn't coming up that far. There's all this wet, muddy sand, but the water isn't reaching it. That means your tide is a little bit lower. So that's a try it activity for next time we all get to go outside. All right, and now on to, of course, these moon phases. So why does the moon look a little different every night? It turns out the moon doesn't twinkle like a star does. It doesn't give off its own light. It just takes sunlight and reflects it towards Earth. So as the moon travels around the Earth, it reflects a different amount of sunlight. Where you see the word new, a new moon, means that all the sunlight reflecting off the moon is shining away from Earth. And the full moon, the opposite side, is when that sunlight is bouncing off of the moon, causing the moon to appear a fully illuminated circle. In between, the moon waxes or gets bigger, and then the moon wanes or it gets smaller. The waxing moon actually comes from the ancient art of candle making, how you can make a candle by dipping a string into hot wax and then cold water, and then back into the hot wax and back into the cold water. And every time you do that, the candle waxes, it grows. So the waxing moon gets a little bit bigger every night. From one day to the next, the change is very slight. That's one day, that's another day, there's another day, and every time I click, we get a new day. The moon getting bigger and bigger all the way up to the full moon. And then it comes back down again. And then it goes all the way back down to a new moon. Now, I don't know if anybody was counting how many clicks I had just there. It would have been very hard to follow. But there are about 29 days for the moon to complete an entire cycle of phases. There's a word for that period of time, and that word is spelled M-O-O-N-T-H. Wait, no, it's not. Moonth? Yeah, that word actually used to have two O's in it. 1 month, that period of time, is approximately how long it takes the moon to go through a full set of phases. We used to call that word a moonth, and nowadays our calendar is a little different. Some months have 30 days and some have 31. But that original term comes from the period of time it takes for the moon to go through a full set. If I connect them all together into one big animation, we can watch the moon wobble through all of its phases. And every time you see a full moon, 1 month has gone by. So there's a new month right there. And then we wait, and then we wait, and there's another month right there. It's a little change from one day to the next, but those changes do add up. And you know what else I notice as we're watching this animation? We always see the same face of the moon. We don't ever get to see what's on the moon's back because the moon is rotating and it's revolving. And those two things are in perfect sync so that as the moon goes around the Earth, it spins so that it always shows us the same face. There is such a thing as the dark side of the moon, but we can't see it from here on Earth. We would need to take a spacecraft, fly it out past the moon, turn around, and take a picture. And that's the only way we know what the dark side of the moon looks like, because we can't see it from where we are on Earth. All right, now we get to our try. Oh, Crystal, did you have a question before we do our
That's
try?
okay. Yeah, we have a question from Jen, and she's asking, what are the darker spots on the moon?
Ooh, that's a good question. So the moon, great question. The moon is made up of light gray patches and dark gray patches. The light gray parts are the craters, the bumpy parts on the moon where rocks have come in and hit the moon. The moon doesn't have an atmosphere like Earth does. So little tiny space rocks that would burn up in Earth's atmosphere, they're actually going to come through and they're going to hit the moon. So all the light gray parts are the craters. The dark gray parts are smooth. They're called seas. They're not bodies of water, but they're smooth patches of the moon's surface where there are no craters. And one of those seas, called the Sea of Tranquility, is where those Apollo astronauts landed on the moon. We're going to finish up today by talking just a little bit about the Apollo program. But now is the opportunity for you guys to try out our moon phases activity. So as Crystal mentioned, if you happen to have a flashlight and a ball handy, it doesn't have to be a styrofoam ball and a pencil. It can just be a ball that's big enough to fit in your hand. And this activity tends to work a little bit better if there isn't as much light in the room. So you might find you want to draw the blinds or maybe turn the light off, or maybe it might help to maybe try this activity a little bit later. But if you want to try out creating your own moon phases, you're going to have two people. One person's going to hold the flashlight and one person's going to hold the ball. And if we take this flashlight and shine a light on our moon, the light is not going to move. The light is the sun, and the sun is not moving in this part of the exercise here. But if I took this sun and shined its light on my moon ball, and then if I took my moon ball and rotated around the room, keeping the flashlight on me, I would actually be able to watch my moon go through a full cycle of phases. So the person who is playing the Earth, who's holding their moon ball out, is going to rotate their body around the room. The person who's holding the flashlight, being the sun, has to stay perfectly still. All right? And if you do that, the person who's holding the moon ball spinning around, you can actually watch your moon go through the phases. You can watch it waxing, you can watch it waning, and you can see that. So the worksheet that we passed out has some information about this diagram too. So we can try that out now, or we can try that out later. I'm keeping an eye on the time and realizing that I'm gonna, oh, Crystal, do you have something to chime in while people are trying out their moon phases?
Yes, I do. So we're getting a lot of questions, and I just want to get a few in there while we're on this topic.
Sure.
So a question from Sophia, what actually makes the moon rotate?
What makes the moon rotate? That's a great question. So the moon has an axis just like the Earth does, and it has a magnetic field just like the Earth does. So spinning on its axis is something that is related to the gravity of the moon, the gravity of the Earth, and the fact that the moon has an axis and a magnetic field allows it to spin on its axis as it's orbiting around the Earth.
And we have another question from D. Can astronauts see the other side of the moon?
So human astronauts in real life, not in the movies, we have never been anywhere other than the surface of the moon. Now, the Apollo astronauts in the early Apollo missions, they did orbit around the moon. So they didn't walk on the dark side of the moon, but they traveled in orbit around the moon a couple of times. So they have seen it, but they haven't walked on it. We've only ever landed and walked on the light side of the moon. The Chinese space program a couple of years ago landed a probe, a rover, on the dark side of the moon. So not a person, but a robot and a spacecraft. So they've been able to see that side as well. But astronauts, if we ever decide to travel further than the moon, we could always look back and see the moon as we're passing it. But very, very few people have had the opportunity to do that.
Cool. So Brian, one last question, then I'll let you continue on. But we had another question. What speed does the moon travel at?
What speed does the moon travel at? That's a good question. In terms of miles per hour, I don't know the number off the top of my head. Because the moon has to orbit the Earth in just 29 days, it is moving very quickly, but I don't know the exact number. I apologize.
That's okay. We can actually, if that person would like to email us the question at the end of the
Yes,
program, we can try to find the
look
answer
that
for
up
them.
and we will follow up for sure.
Great.
All right, now on to one of my favorite subjects. Eclipses are rare, unique events that happen because we have a moon that is 400 times smaller than the sun and 400 times closer. Every once in a while, things line up just right where the sun and the earth and the moon kind of get in each other's way. And there's two different kinds of eclipses. When the moon gets in between the sunlight, blocking the sunlight from reaching Earth, we call that a solar eclipse. When the Earth gets in the way, and what should be a full moon is actually the moon getting all of its light blocked out by the Earth, that's what's called a lunar eclipse. And these events are pretty rare, but you may recall there was one just a couple of summers ago, the 2017 eclipse that went across the United States. We did not see that. We saw about 70% eclipse. It was like a crescent sun because the sun was partially blocked out. Some of you may remember that event from just a few years ago. Now, what's happening 4 years from now is another total solar eclipse. And check out where this one is going. It's starting down in Mexico, arcing across the United States, and it's not going through Connecticut. But for my friends who are visiting us today from New York and New Jersey, boy, you guys are getting front row seats to this next eclipse. Here in Connecticut, we're going to see a 90% solar eclipse on April 8th of 2024. So if you have the opportunity to travel to one of those towns along that line, or if you can even get close, you can get to witness one of these really, really rare events. Now, if you want to figure out how an eclipse works, we can use our flashlight and our styrofoam moonballs. Now, normally, I wouldn't tell you to look directly at a flashlight. That can be very dangerous. But if I take my styrofoam moonball and hold it in front of my flashlight, I can turn that flashlight on and I don't have any light shining in my face right now. The moon is actually blocking all of that sunlight from reaching my eyes. So right now, this is a solar eclipse. I'm the Earth, we have the moon, and then we have the sun, which is my flashlight. The other example would be the lunar eclipse, where I'd be looking at what should be a full moon, but if I put my head in the way, now all of a sudden my full moon is actually a great big shadow because my head is blocking that sunlight. So that's what's called the lunar eclipse. So with something as simple as a flashlight and a ball, we can try to simulate all these different happenings with the moon phases, with eclipses, and those kind of events. Really, really neat stuff. Oh, I think somebody just drew on my screen. That's okay. We're going to finish up today by talking about the past and the future. So how do we know so much about the moon? Well, we know because we went there. Back in the 1960s, when the United States and the Soviet Union were engaged in the space race, we were trying to see who could explore space the fastest. And the Soviets were the first people to put a person in outer space. And we decided we were going to be the first ones to land on the moon. And we did. 50 years ago, in the summer of 1969, the Apollo 11 mission brought Neil Armstrong and Buzz Aldrin and Michael Collins to the surface of the moon. Those spacecrafts were called the Apollo mission, and that comes from Greek mythology. Apollo is one of those ancient Greek gods. And I tell you, NASA, they're really, really great at coming up with clever names for things. So the Apollo mission was the past. Artemis is the future. And if you're familiar with your Greek mythology, Artemis was actually the twin sister of Apollo. So we're taking these names and we're reusing, well, not reusing them, but finding new and clever ways to use them. So the plan for the Artemis program is sometime in the next 5 to 10 years, we are going to go back to the moon because we stopped. You know, the Apollo missions ended in 1973, which means it's been 47 years since we went back to the moon. Now, we've done so much in those 47 years. We've landed rovers on Mars. We've put spacecrafts into Saturn's rings. We've explored outer space. We put the Hubble telescope up there to look into other galaxies. But we haven't been back to the moon. So the Artemis mission is going to go back to the moon, and not just for a day. We're going to see if humans can live on the moon for days, for weeks, maybe for even longer than that. Of course, there's no water on the moon, so we're going to have to make some big plans and really figure some things out. But this Artemis mission is the new, exciting exploring of the moon. So, as our program winds down here, I have one more triad activity. This one is a big one, and it's going to take a little bit of time. In 5 to 10 years, when NASA's getting ready to go back to the moon, they're going to be looking for astronauts. And I don't know about you guys, but I'm going to be a little bit older 5 to 10 years from now. Some of you, however, might be in high school. You might be in college. You might be studying science more. So if you would like to be one of the next people to take small steps and giant leaps, just like Neil Armstrong did, then this triad is a big challenge. Because if you want to continue studying outer space, you can be one of the next people to travel to another world other than Earth. And that actually brings me to the end of my slides and my presentation. I'm going to check in with my friend Crystal here to see if she has any wrap-up questions for me.
Hi, Brian. Thank you. Yes, we actually did have a few more questions that I've been collecting as you've been talking.
Okay.
So one of the questions we got from a couple of different people, would it ever be possible for the sun to move?
Ooh, good question. So the sun and the stars are not really moving, maybe the tiniest little bit. But what's ultimately happening is everything in our galaxy is being held in a balance. And scientists believe that at the center of our Milky Way galaxy, there is a black hole. We can't see it and we can't go there, but that black hole has just enough gravity that it is holding things. It's holding all of those stars in place. Now, if we look at the night sky, and astronomers have been looking at the night sky for hundreds of years, over a really, really, really long period of time, there is a little bit of motion in the stars. Not a lot, just a little teeny tiny bit. So our sun is moving very, very slightly and very, very slowly. But in our lifetime, it's not going to move to the point where we're going to notice anything. Because even if the sun goes moving around in our galaxy, the planets are still going to keep going around the sun, and the moons are going to still keep going around the planets. So everything is kind of still held together in a balance.
Great question. Our next question is, why does an eclipse only happen every 4 years? Is there a purpose to the eclipse?
Yeah, so the reason that eclipses are rare and the reason that not every full moon is an eclipse is because of that tilt of the Earth's axis. So if you could imagine the, let me go grab my flashlight, my moon ball real quick. So I've got it lined up right now where the sun and the Earth and the moon are all on these perfect planes with each other. But if my sun was back here shining on me, the moon's orbit around the Earth isn't a perfectly flat circle. It goes high and it goes low and it goes high and it goes low. So not every full moon is an eclipse, but every once in a while, when things line up just right, and they aren't predictable, that is the thing, is we can actually look at the way the moon is moving and the way the Earth is moving. That's how we know that there's going to be an eclipse in April of 2024. Because while they are rare events, they're predictable events. If we watch the motion, we can kind of roll the clock ahead and make a prediction about what'll happen next.
Awesome. Thank you, Brian. Just a couple more. To continue on with the sun, because we just had another question about the sun. Do you think the sun will be tiny in a few hundred years?
Ooh, okay. So as far as the sun's size goes, people often ask me in the planetarium about, the timeline of our sun. Now, I want to preface this by saying I don't want anybody to lose any sleep tonight because our sun is not going anywhere anytime soon. Based on how big our sun is compared to other stars, we think our sun is going to last for about 12 billion years. We think it's only 4 billion years old. So our sun is not going anywhere for a really, 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 really long period of time. Now, if you're curious, 7.5 billion years from now, when our sun is starting to get towards the end of its life, it actually will get bigger before it gets smaller. So the first thing our sun is going to do when it gets to the end of its life is it's going to swell. And it's going to swallow Mercury, and it's going to swallow Venus, and it's going to make things really, really hot on planet Earth. But again, this is not happening tomorrow. It's not happening next week. 7.5 billion years from now. So we don't have to worry about that or lose any sleep. But the sun actually will swell and get bigger before it shrinks down and ends up, eventually it's going to end up kind of like what happens if you don't add wood to a fireplace. The fire will eventually get slower and lower and lower, and it'll be just this little tiny ember, and then it'll just go away. But before it does that, it is actually going to swell a little bit. Don't worry, really, really long time from now.
Thank you, Brian. That's such a relief. And then we have one more question from the audience, and then we'll probably wrap it up because we're almost exactly at 1 hour. But the last question is, do you think that there is life on Mars?
Ooh, that's a good question. So I don't know, of course, I'm going to have to throw a theory out here. My theory is that if there is life on Mars, it exists as little tiny microscopic organisms, maybe living in the water. Mars does have water below its surface. And so I think that there are little tiny, but I don't think there are aliens walking around on the surface of Mars. And my proof, my evidence there is the Mars rovers that have been taking pictures and sending us video have not encountered any animals or any plant life. But because there is water below the surface of Mars, I think that maybe, just maybe, there might be some little tiny organisms.
Awesome. And so I think that wraps up all of the questions. I just want to thank everybody here for joining us this morning. And we're going to be having more programs coming up from the planetarium. But I wanted to let you know that this afternoon at 2 o'clock, we're going to have a special program with Sarah Clement from our preservation shipyard. And she is going to be teaching everyone how to tie knots. So please tune into that program this afternoon. It's for kids of all ages, from 5 years old to 88 years old and above. So please join us if you would like to know how to tie knots. Come with some rope if you can, and we'll practice tying knots. But we'll also have more programs coming up, programs at 10 and 2 every day this week. So please check out the email that I sent to your parents, or the Facebook appointments, the Facebook events that I've been posting on Mystic Seaport's Facebook page, Mystic Seaport's Educators Facebook page. And again, just want to thank everyone for coming. I'm going to put our email addresses up right here. So if you have questions, I am putting them in. I'm putting our emails in the chat box. And I see something about recording of the presentation. If you email me, I will send you a recording of the presentation. Absolutely. Just a second. It's hard to type and talk at the same time. All right. So Crystal.Rose and Brian.Kohler@mysticseaport.org. Thank you so much for joining us, everyone, and I hope that we see you this afternoon at 2 o'clock. Have a great day.
Bye. Thanks, everybody.
Thank you, Brian.